It's like there's this ring around a star. It's like the poster child ring, planetary ring, and it's got a little planet that they identified. I think it was 2006, and it was like the first Jupiter that they ever found. But then they started taking spectra of it, and it turned out it wasn't a Jupiter at all. It looks like it's just a cloud of dust. So, but it still might be a planet, right? It's just shrouded by dust. It's only reflected in starlight. There's no thermal energy whatsoever. So we're trying to put together a scenario for maintain the dust over the lifetime of the star, or at least something more than 10 years. It's hard, it turns out. Hey, how are you?
He said, what's that thing? Given the choice. Definitely better. Definitely better.
This guy just looks at it like the
Okay, so the original speaker for today could not make the trip. So that's the third cancellation in this semester, and we are not very lucky. But on the other hand, we have opportunities to learn about the great work done by our own professors. And today, it's a pleasure to have Professor Ben Bromley give the colloquium. So Ben obtained his PhD from Dartmouth College, working on large-scale structure in the universe. He then moved to Los Alamos National Lab and Harvard University as a postdoc, and he joined the department about 16 years ago, as a faculty member. And Ben has a really broad research interest, and he's an expert in planet formation and relativistic astrophysics about black holes, galactic dynamics, and also computational astrophysics. And today, Ben is going to tell us about hypervelocity stars.
Thank you, Zheng. Yeah, I'm sad that Hal Levison couldn't join us today. I was really sad about that about 4 hours ago, too. Okay, so I'm going to talk about hypervelocity stars, and I guess at the outset I should just give you a working definition of what I mean by a hypervelocity star. And in the context of current observations, a hypervelocity star is any stellar object that's moving fast enough to escape the galaxy, the Milky Way galaxy. And just to put that in context, the speeds that we're talking about for typical distances that where we measure these objects, roughly 500 to over 800 kilometers per second in the rest frame of the galaxy. So actually what I'm showing here is not a hypervelocity star at all. It's another galaxy which may have an extraordinarily massive black hole in it. And I'm going to start off this talk just by mentioning a few things about supermassive black holes. Because I'll try to convince you that there's a connection between hypervelocity stars and the supermassive black holes that we find in the centers of many, if not virtually all, galaxies. So about a year ago, Anisotropy organized a really, really excellent conference on black holes, including supermassive black holes, and the discussion really came down at some level to arguing about details, what connections can be made between black holes and the environments in which they live, the galaxies that host them. And it was really an amazing conference, and it hit me as I was preparing this talk how far we've come in our understanding of supermassive black holes in general. And I thus went down a road of sort of historical traverse, and I wound up here in the late 1950s thinking about the first observations that led us to our current understanding of supermassive black holes. Back in the late 50s and early 60s, people were trying to understand the extraordinary amount of radiation that was being pumped from objects that appeared to be of the dimensions of stars. So this, one of two sort of the first objects to be detected in radio with these gargantuan luminosities, is the source 3C273, and it is located at a distance of roughly 750 megaparsecs. Now, a parsec is a unit that I'll use in this talk, and it's roughly 3¼ light years, and it characterizes the distance between stars in the solar neighborhood. So 750 million parsecs, or roughly 2.5 billion light years, is a cosmological distance. This object clearly was among the distant galaxies, and the amount of radiation it was dumping out was roughly 1 trillion times, or more than 1 trillion times, the luminosity of the sun. The thing that must have been just mind-blowing for people who were studying these objects was the way, not only the amount of light, but galaxies can pump out, they have a lot of stars, they can pump out a lot of light. What was astounding, at least I would have just curled up in a corner and sat at the base of a tree and contemplated this. The light varied significantly on time scales of months. Okay, in a sort of in a way reminiscent of some single coherent entity, so that the only interpretation of this variation could be that the physics was taking place in some local region of space that was causally connected by this time, by months. So the physics was taking place on a scene of light months, or less than a parsec, less than the distance between neighboring stars. And the amount of radiation coming from that small distance is unfathomable, or at least was, until the 1970s, when people began to put together a picture of powering these objects known as quasars with supermassive black holes, things 100 million times the mass of the sun, that draw energy from gas in their environment as that gas gets crushed through the gravitational potential well of this massive object. So this was the beginning, and as people studied these objects, they realized that the presence of supermassive black holes was actually quite commonplace, that many, many galaxies hosted such things. And a natural thing to do when you have that realization is to say, well, I live in a galaxy, so maybe my galaxy has a supermassive black hole too. It turns out, however, that our galaxy has a lot of dust in the direction where the center of the galaxy is, roughly 8 kiloparsecs, or 27,000 light years away from the sun. It's very hard to see in there. So it wasn't until the 70s when people began to pull evidence from the center of our galaxy for the presence of a supermassive black hole. And what we found, by comparison to what I just showed you, was particularly unstunning. The luminosity coming from an object tentatively believed to be a black hole was relatively low, 1,000 times that of the sun. Stars can do that. The time variations indicated that yes, this amount of radiation was coming from a small region, but there were hints in the spectra, the types of radiation emitted, that this was a really interesting object, and people began to build the case for the existence of a million solar mass black hole in the center of our Milky Way galaxy. And however, the evidence was really slow in coming because this region is so hard to observe, and black holes themselves are kind of tricky to identify. In terms of their existence, we only get information from the material swirling around them. So I think that as time went on and more observations were made, there wasn't a real coup until this work. People in the 90s began to look in the infrared at very bright stars in the center of our galaxy. Many of you, if not everybody, has probably seen this animation showing stars, stars located in the plane of the sky, observed in the Galactic Center, bright, mostly B stars, I believe, in the Galactic Center. And what you're going to see, if I can get the animation to work, it's been iffy today, I think it's humidity, is the stars moving in sort of a time-lapse series on nearly perfectly Keplerian orbits. When I first saw this, I didn't cry, but I felt I should tell everybody that I cried because it was just, it was so beautiful and remarkable. Stars in my lifetime I don't generally think of as moving in the plane of the sky, and yet they move. Yeah, it's nice. Yeah, that's right. It's just beautiful. And yet there is nothing pumping out any radiation in infrared light that we've detected, at least at the level of a star like this, at the putative center of mass for these Keplerian orbits. Just amazing. From my perspective, this is the best evidence for the existence of a black hole that we have as...
How much of those orbits have we actually seen?
In some cases, complete orbits.
Really?
I should have a better answer for you, but I think it's just 1 or 2 cases.
Oh.
There are some orbits that, while not complete, are absolutely spectacular. There's one, I don't know if it's in, that just whips right on around. It's just beautiful. They have 3D information on these orbits, so these things are very well characterized. It's very well known what is tugging them around. Really beautiful.
Is there something like a length scale, a scale of what would
So
you see there?
the closest approach is sort of outer solar system distances, 1,000 astronomical units.
Okay.
So more like tens of thousands astronomical units, I think, is typical. Of
The
what we're seeing.
seconds of arc, is that what Christoph is referring to?
The arc seconds were what was listed there.
Oh, okay, and the date, these were years. This is basically a period of, if I saw that correctly, nearly 20 years or so.
Yeah, that's right.
That was covered.
Yeah, yeah. So it's really cool. So these data that I just showed you were not available in the early 90s. When Jack Hills, a research scientist at Los Alamos National Laboratory, began to think of ways of identifying or at least proving the existence, inferring the existence of a supermassive black hole in the center of our galaxy. So he came up with this plan. Okay, if it's really hard to see into the galactic center, maybe we can see stuff that gets flung out of the galactic center from the the region of the black hole that wouldn't be flung out if that black hole didn't exist. So his idea was this. Suppose you have a binary star. Turns out most stars are binary stars, or many stars are come in pairs. And so that's not an implausible thing. What if a binary star got close to the black hole, and what if the three-body interactions led to an ejection of one of the binary partners, just following conservation of energy and angular momentum? Jack Hills ran the simulations. He ran these three-body experiments, and he verified what he undoubtedly already knew from the energy conservation estimates, that the speeds at which an ejected star could be ejected with were enormous. Okay, thousands of kilometers per second. I've run the simulations myself. I've seen them go up to, for reasonable conditions, 5,000 kilometers per second. That's a good clip. So Jack Hills thought, okay, great. Okay, all we need to do is sit out here and wait for these stars to rip by us. And then we'll be able to say, yes, there is a supermassive black hole in the center of our galaxy. And since this is a Department of Astronomy and Physics, I thought I'd better put this kind of interaction into a visual language that you all would better understand in terms of a Feynman diagram. Evidently, some of the interactions were done in a zero gravity or microgravity environment. So here is now, I'm going to give you an overview of what I will cover for the rest of the talk. I will give you a little more background in hypervelocity stars, just what's involved in getting us from this interaction with the black hole that I mentioned out to where we can actually see them. And in that process, I'll talk about how we might use hypervelocity stars to map the distribution of matter within the galaxy. It turns out the outer regions of our galaxy, the galactic halo, contain an awful lot of dark matter, and we don't exactly know how that dark matter is distributed, much less what it exactly is. Then I'll take a foray into the discovery of hypervelocity stars and the observations. And if there's time, I'll put in a plug for the connection between hypervelocity stars and a possible mechanism for growing supermassive black holes. Okay. So here is another schematic of a hypervelocity star being produced. You have a binary star coming in. There's a separation between the binary partners designated by A. These are typically solar system type distances. So 1 AU, a fraction of an AU for a tighter binary. M1, M2, think the mass of the sun. The stars come in within a few thousand to hundreds of astronomical units of the massive black hole. One star gets flung out, the other gets captured. I tried to think about how to explain that process, and I can use words like bolo, those things that, yeah, so I could use that. That's not entirely physical. You can talk about conservation of energy and angular momentum for sure. That's the safe bet. But here, as a dynamicist, as someone who runs simulations, has recourse to actually someone who runs simulations, this is my perspective. What happens to these stars is they're orbiting about each other, and then they get close to the black hole. All of a sudden, or there is a point when those stars just don't know that they are together as a pair, because the black hole gravity is dominating their dynamics. They get frozen at some instant in time with new Keplerian parameters, depending on how they were spinning when they hit this region of strong gravity. They got frozen with new Keplerian parameters, and those parameters will put one star on an ejected orbit and the other one on a bound orbit around the black hole. When they get disrupted, when there's a binary disruption event, they simply don't know their partners exist. Okay, and that's more or less what happens. They get in, they get locked up, and then they just do their thing. This doesn't always result in a disruption. Sometimes, after they emerge from the system, their orbits were oriented in such a way that they come out still bound. So it's a little bit of a crapshoot as to whether or not the stars result in a hypervelocity star and a bound partner, or just back in a situation where the stars are in binary orbit again. Okay? And all these outcomes depend on the masses of the black hole and the stars, their binary separation, their orientation, and the distance of closest approach. How close do they get to the black hole? So we can put all this physics together. It's ideal for simulation, and that's what we do. This picture I just have as an illustration for one specific choice of impact, or of closest approach rather, and binary separation. I just show you the variation that comes about just from reorienting the orbit of the binary as it flies in toward the black hole. Okay? I have a code that sets up things that orient these binary systems randomly. It puts in the distribution, a reasonable distribution of binary separation, so I vary that. I put in a realistic range of stellar masses and closest approach distances consistent with a random encounter. And I have a code that I call a fountain that just sort of spits out random hypervelocity stars, and that's the best graphic I could get for that. But that is not the end of the story. For hypervelocity stars to be interesting for us here on Earth, we need to think about what happens to them after they leave the galactic center, after they leave the vicinity of the black hole. We're unlikely to ever see an actual binary disruption in our lifetime. They happen fairly rarely, at least on human timescales. But the stars will take a long time to traverse the distance of the Milky Way galaxy, and these stars are going really fast. So they're going to get a very, very long way away. So the next part of what I'll talk about is how you move through a galaxy, what it means for a hypervelocity star to travel through. So what is our galaxy? This is my cartoon. I really had my PowerPoint game on here, evidently, of the Milky Way galaxy. It has three components in addition to the supermassive black hole at its center. It's got a sort of spherical, dense cluster of stars, roughly 1 billion stars, concentrated in the center, known as the bulge. Out where the sun lives, in kiloparsec distances, is the galactic disk. This is probably 10 times the amount of mass in the disk as in the bulge. The bulk of the matter in the mass in the galaxy, however, resides in the galactic halo, which can be quite extended, hundreds of, or 100 kiloparsecs, certainly tens of kiloparsecs. And I just throw out this small little equation here showing one possible way in which the mass density in the halo might fall off with distance. It's typical of other galaxies, and we assume, though our perspective is not ideal for making measurements, we assume that the fall off is like, at least over some range, like 1 over r squared. And so I'll just throw that as a baseline and come back to that in a sec. Now, this idea of using objects that travel through the galaxy as a way of sort of mapping out the mass density of the galaxy is not new. And I'm only going to highlight a couple of local examples of how this can be done. Ben Kaya has been working on a project to track photons traveling through the galaxy's potential well, and to map out how the small deflections from the galaxy's potential can affect the glow of the Big Bang in the cosmic microwave background. And what's shown, don't worry about the meaning of the colors. What's shown is sort of gives you an estimate of the magnitude of effect. Bright and dark are indicate larger effects, whereas neutral gray is no effect at all. Just will tell you the impact of the galactic potential on modifying the effective temperature of the photons as they traverse in from the outer cosmos to us in the galaxy. This little bump here, Andromeda.
This is the effect is just like a V over C squared, effect. It's like 10 to minus 6 on the temperature.
Smaller even. Yeah, that's another story. But yeah. Another example is a cluster of stars known as Palomar 5. And Zheng introduced me to this really cool object. It's a cluster of stars that's taking a fairly wide sweep through the galactic potential, and as it sweeps in toward the galactic center, the stars get kind of peeled off, and they end up on independent orbits that are free to drift along as this cluster continues on its path. And after multiple orbits, this long extended tail of stars can be seen, and the nature of this tail will be sensitive to the galactic potential and the details of the orbit of this object. The upper plot is actual data. The lower plot is an n-body simulation, indicating that I hope we're at least on the right track.
So this is a snapshot that
Yes.
assumes in the simulation that it started as a localized cluster and then it spread out as it traversed. But you're not watching it traverse.
We're not. So you nailed it exactly. This is a snapshot. Our assumption was the cluster started off spherical, and these stars simply spread as they went through.
There must be some degeneracy with the number of passes now.
Yes. Yeah, I think the parameter space is pretty tough. Yeah, that's another subject. It's fine. So let me do the same thing with hypervelocity stars. Let's shoot them out from the center of the galaxy and see what happens to them as they traverse into the galactic halo, slowing up as they're climbing out of the galaxy's potential well. These different lines correspond to different models for the galaxy, and you can see, in general, things simply slow down, as expected. So you actually, in order to escape the galaxy, you have to get flung out with a relatively high speed from the galactic center. So things flung out at 1,000 kilometers per second from the galactic center will fully escape the galaxy, even though their speeds out in the galactic halo may be significantly lower. Now, in order to take the next step of kind of deducing anything from the observed hypervelocity stars, I need to introduce a little bit of stellar physics, just a little bit. Stars are our tracers. Okay, they have specific properties, and I focus mostly on stars, or entirely in this talk on stars known as main sequence stars. These are stars in stellar adulthood. Not that adults are ever stellar, but these stars represent objects that are going through a very well understood process of burning nuclear fuel on their way to some either explosive finale or some cold, quiet demise. The numbers, the equations that I've written up here indicate two things. First of all, the top equation, the luminosity of a main sequence star goes as a pretty high power of the mass. So something 10 times as big as the sun will burn thousands of times more brightly. Because of that high power output, it means that the fuel is being burnt at a very high rate. Hence, the lifetime, the amount of time that the star spends in adulthood is relatively short in this equation. So something 10 solar masses, it turns out, will wind up only being on the main sequence, as it's called, being an adult, for roughly 30 million years. Compare that to the sun, which will be on the will be like as it is today, roughly, within a factor of 2, for 10 billion years. The other thing that we do take into account, although I use it less here in this talk, is something known as the initial mass function, which just tells you the distribution of stellar mass when stars are fully formed. And this function indicates that low mass stars are much more likely to be formed than high mass stars. Most of the mass in stars is in the form of low mass stars, and I'll allude to that in a little bit. The final sort of random fact that I've mentioned is that many stars reside in the form of binaries. Okay, so let's see what happens to a population of stars that travel through into the galactic halo from a binary ejection, from binary disruption, following Jack Hill's mechanism. The plot that I'm showing here just lists histograms, number of stars, for 2 different populations. These are relatively high mass stars, 4 solar masses. And the blue population are things that are close to us, nearby stars within 30 kiloparsecs. The magenta objects are those stars further out. So the interesting thing about this plot, because the lifetime of the stars is short, the only stars that make it to high distances are the ones that were ejected at high speed. If they didn't get high speed, they wouldn't live long enough to reach the outer regions of the galaxy. It's as simple as that. It's straightforward, but the cool thing is that you can actually make quantitative statements about the distribution of mass in the galaxy, even on the basis of a very few number of stars. For example, the plots differ because of how sort of compressed the mass in the galaxy is. That parameter alpha that I said was 2 in the mass density profile for the halo is listed here from a range of 1.8 to 2.5. I won't go into details, but the fact that all the velocities are shifted to high speeds in this case where the mass is more concentrated means, on the basis of we did it with half a dozen stars, eliminate an entire class of models of the distribution of mass in the galactic halo. I think that is pretty fun. This was a slide that 5 years ago I never would have dared to put up. But one thing I noticed in my simulations is when I throw a binary at a black hole, it comes right back at me, the ejected hypervelocity star. The way the dynamics works, when the eccentricity, if you will, like a comet of the binary, results in ejection that's pretty much right back at you. Okay, so if you see a hypervelocity star following a certain path, it's very likely that the incoming binary was in the opposite direction. That means that the location of the binary of the hypervelocity star is a flag as to the location of the progenitor, the binary star that we saw. So that gave rise to the hypervelocity star. So I give you 2 examples. One is my favorite scenario in which binaries randomly encounter the black hole and hypervelocity stars randomly populate the sky isotropically. Here is a theoretically distasteful model in which all the hypervelocity stars lie in one region of the sky, indicating that all the binaries came from one direction. Maybe you can think of a cluster of stars like that Palomar 5 I showed you, but that barreled into the black hole, and all the hypervelocity stars got kicked out the other direction. So this is where we stand right at this point. Hill's mechanism is the idea that hypervelocity stars are a natural byproduct of a binary disruption by a supermassive black hole. The speeds that are possible are sufficient to escape the galaxy, and the distribution of speeds that we observe can provide interesting constraints on the potential of our galaxy, the mass distribution of our galaxy, the configuration of binaries, it turns out, and the stellar properties of things that live in the center of our galaxy. And again, the sky distribution is an indicator of where those binaries existed. So I'm going to move on to the discovery. 2005, almost 20 years after Jack Hills made his prediction, Warren Brown and collaborators were looking at, I don't even know what. I don't know if anybody can remember now, because what they found was a blue star that was cooking 700 kilometers per second in the rest frame of the galaxy, sitting out at 55 kiloparsecs. Fairly young star. It's 3 solar masses. It has a 300 million year lifetime. The likelihood that it was formed out where it was observed at 55 kiloparsecs, as far as we know, 0. So when they did the calculation, sure enough, its 80 million year travel time estimate from its observed location to the Galactic Center is consistent with its 350 million year lifetime. The picture is perfect. It's great. And since that time, there have been 16, 17, 18 more discoveries. The most recent one is cool. From the Large Sky Area Multi-Object Spectroscopic Telescope, LAMOST, a new result has been published by Zheng and collaborators. Zheng has discovered a 9 solar mass star, main sequence star, going at 477 kilometers per second. It's the closest bright hypervelocity star we know of. The travel time to the Galactic Center is 32 million years. Okay, now I have to take a little deep breath, because 32 million years is dangerously close to the 30 to 40 million year main sequence lifetime of this star. But I'll ask your opinion. I'm willing to swipe the sweat off my brow and go with it. However, as Zheng points out, this star is very similar to another hypervelocity star, colloquially known as HVS3, which does have a really serious problem, hinted at by Zheng's star. The problem with HVS3 is that it has a 100 million year travel time, and its main sequence lifetime is about the same as LAMOST HVS1. This is unacceptable, unfortunately. We can't simply have the star be ejected from the Galactic Center before it was born. There are contortions of stellar evolution that may save this object and the model of Jack Hills, but we also must consider for this object the fact that there are alternatives to the binary disruption process.
So how are you measuring the velocities of these things?
We're measuring redshift. And in the case of...
You got the angle and everything? I
we
mean,
know where in the sky it is?
Yeah, you know where, but you don't know whether it's going, you know whether it's approaching or, but at what angle? I mean, it isn't going directly away from you, so you don't.
That's an excellent point, and I'll try and close with exactly that point with an upcoming mission that we're looking forward to very much in this business. Zheng was careful to try and address your point that this star may be moving in the plane of the sky. It's more than just the recession velocity that we can easily get, well, that one can get from spectrum. This plot is an indication of where the star may have originated from doing just that measurement. The interesting thing about the upper plot here is that it shows the distribution on the plane of the sky of all the known hypervelocity stars in magenta, with LAMOST HVS1 in the red star, as shown. This is a far cry from being an isotropic distribution on the sky. Okay, these hypervelocity stars seem to have come from somewhere. They seem to be correlated with something in the galactic center.
Galactic coordinates or celestial coordinates?
This is galactic. So let me superimpose what people think. The curves that are shown indicate the sort of sky projection of structures in the galactic center. And I'll try to illustrate it here. I don't have these angles correct, I'm certain. But the idea is as follows. there is a circumnuclear disk of a few parsecs in radius in the galactic center, and it seems that the plane of this disk and the location of those stars line up. So it's possible that those stars originated from this circumnuclear disk of stars. The uncomfortable part about this is that the dynamical times of this circumnuclear disk, if my back of the envelope calculations are correct, are hundreds of thousands of years, which is nothing. The flight time for these stars is hundreds of millions of years in some cases. So it's really uncertain that such a structure like this could persist for so long. So this would be a theoretical challenge that we have to meet. Okay. The final thing that I want to do is make a case that there's one other thing that the hypervelocity stars and Jack Hill's mechanism can do for our understanding of supermassive black holes. And this I entered the domain of speculation, the real hard speculation. The slide, the animation that I showed you earlier, consisted of a bunch of stars, half dozen or dozen stars, moving around in tight orbits around the black hole. I've given you right off the web illustration of these stars here. The other thing that I mentioned to you was that binary disruption and the production of a hypervelocity star also involves the capture of of the binary partner on a bound orbit around the black hole. And it turns out that the orbital distances of the final, of the captured star is sort of comparable to those S stars that we observed in the galactic center in the animation. The S stars themselves are on a variety of eccentricities about the central black hole. The hypervelocity star partners are always captured on high eccentricity, but the stars can interact with each other, and they can diffuse orbitally in space, and hence we can make a case, and many, or at least several authors have, that the S stars, the stars that we see in the galactic center, very near the black hole, are the captured partners of hypervelocity stars. And one thing that I just want to put up here is when we run our code, we put in everything we can about the lifetime of the stars, the time of flight of the stars. We get we infer a production rate for the hypervelocity stars, and that's identical to inferring a binary disruption rate, and that by definition also tells us the deposition rate of stars in the galactic center. And when we use a reasonable initial mass function to predict how many of these bright stars we might see in the galactic center, we get a number that's the same order of magnitude as what's actually observed. So these two numbers, the S stars, meaning the stars stuck in the galactic center that we observe, and the hypervelocity stars that we see, are eerily similar. Okay, it doesn't mean it's not enough to convict, but you know, if the two processes, the presence of those S stars and the production of hypervelocity stars, really had nothing in common, there's absolutely no reason why those numbers should be anywhere near each other. So we would be remiss if we didn't at least follow up on the implications that these objects have a common origin, that binary disruption is reasonable.
Doesn't that imply that your samples are equally complete?
We try to put in what we can. We know what the selection is on the hypervelocity stars. We know how to cut out. We know what we are able to see, and we do the best we can for what's observable in the galactic center. We assume that everything above a certain brightness is actually observed within we're talking 20 stars, so it's not as rough as.
So what are the chances that you have all 20 hypervelocity stars? What's the selection for finding those?
Well, the surveys are well defined in terms of what they're looking for. So Warren Brown can fold in the results of our simulations, which pump out everything, into the selection of the surveys. Where we really messed up initially, and that's me, was the assumption that these things were distributed isotropically. And the surveys were looking at specific regions, and it almost looks like they got lucky, because they were looking at these, what's turning out to be the stripes where the stars actually are observed. So that's been the toughest part for this kind of argument.
Doesn't that predict an anisotropy of the orbits of these S stars?
Yes, it would as well. However, the orbits of the S...
correlation there.
The orbits of the S stars are rough because they're the tip of the mass iceberg. And so I get to mention that point. There are other lower mass stars that we simply don't see, and it's undoubted that their orbits...
And they're messing with each other.
Their orbits will cause each other to diffuse throughout the parameter space. Okay? One thing that I just want to mention, and I'm going to have to actually probably leave it with this thought. If you use the inferred binary disruption rate of 1 every 1,000 or 1 every 10,000 years, which is more reasonable now given the anisotropy, and you try and estimate the total number of captures that have occurred over the lifetime of the galaxy, you get a modest 10 to the 6 solar masses of captured stars. Well, oddly, that's the mass of Sagittarius A star, the black hole in the center of the galaxy. So although I can't make a case for the binary capture or the binary disruption process for being the source of the black hole mass, because the black hole had to exist in order to disrupt the binaries, I can at least make the case that the binaries contributed to the mass of the black hole. Okay. I wanted to just put this out if you're skeptical about the captured stars actually moving onto orbits where they can be accreted by the black hole. And I'll leave it with this image from the BBC series Sherlock of a bathtub filling up. For every hypervelocity ejection that's happened throughout the age of the universe, there's been a captured star. There's an accumulation of stars, and eventually the stellar density will get so great that they'll have to push each other around. They'll have to be pushing each other onto the black hole at some particular rate that ultimately will equal the rate at which they are accreted. That argument plays really well with dynamicists who are just stuck with it. In order to put this on firmer footing, Leah Papadopoulos in our department has been starting on simulations that track how the stars perturb each other and how this diffusion process and perhaps an enhancement of the binary capture rate by the black hole can take place. And since I'm talking about stars being accreted by the black hole and causing black holes to grow, let me just put in a plug for a recent celebrity, a certain cloud called G2, Gulf Stream 2, I have no doubt. It's in the news. Apparently, as we speak, we're at this panel here. This is a cloud of gas, roughly it's a few to tens of Earth masses in size, that's on a collision course with the black hole in the center of our own galaxy. And apparently, it's going to be spectacular. I think we're here. The press releases will probably come when we're closer to this. But look for it. I think it's really cool.
Is that fast?
It's order months, yes. So, the remaining slides that I have are showing sort of models I have for black hole growth. And I will skip over them and go instead to the future. You had mentioned that it was difficult to see the three-dimensional velocity of stars and really to understand where they came from. It's important to really understand where they came from. It's important to get that information. The satellite's been launched, Gaia, that promises 1 billion objects mapped out in 3D. There'll be millions of stars in the galaxy, mapped out with angular resolutions of milliarc seconds. I tried to come up with an anecdotal example of what a milli-arc second resolution meant. And the best I could do is if you're sitting in Wendover and you're holding up an object, you'll be able to see it from here. And I think if that object is a dime, I think you might even be able to see the date. So it's so with that type of resolution.
There aren't any dimes in Wendover.
That's right. With that resolution, we will be able to see if the predictions of Jack Hill's hypervelocity star model hold, because we will have predictions for the fraction of stars mapped out with certain measured proper motions, which is basically velocity across the plane of the sky. And we'll sort of have these types of maps done for different types of binary interactions, so we'll be able to put the theory to a test. There are many, many lower mass stars out there that we would predict to have undergone tidal disruption and be floating around the galaxy. They live a lot longer, so their distribution in the galaxy will be much richer. And hashtag Gaia. Can't believe I said it.
You're actually going to measure the transverse velocity of these things in real time.
Well, yes, so they'll repeatedly measure these stars' positions with high accuracy over a period of time, and they'll be able to understand how fast they're moving in the plane of the sky. Okay, so to conclude, binary disruption is a reasonable mechanism of the production of now observed hypervelocity stars, warming theorists' hearts because the prediction predated observation by almost 2 decades. There may be other mechanisms at work for producing these stars. That's the caveat. There's still mystery involved, even if the mechanism works, because of the anisotropy of the hypervelocity stars on the plane of the sky. I urge you, though I didn't really make the case strong here, to not forget the connection between hypervelocity stars, the S stars in the center of the galaxy, and it turns out the tidal disruption of stars around black holes in other galaxies, and see how this may fit with the growth of supermassive black holes. As I said again, right now we're seeing only the bright stars. Gaia will change all that. We'll get a much better sample of what's out there with Gaia in the next couple of years. And in case I was more effective than I realized in promoting the tidal disruption, binary disruption mechanism for generating hypervelocity objects like I've discussed, I just want to put up this snapshot of a paper that came out last week. A globular cluster, if I may read the title, toward M87 with a radial velocity less than 1,000 kilometers per second. The first hypervelocity cluster. How that happened? Not sure. Thanks a lot, guys.
Okay, questions?
So I imagine there's probably a serious observational bias in where you're going to be able to see these things because of the way you can see the redshift. Would that be built into the anisotropy you see at all?
People who do this carefully,
Okay, I was thinking
yes.
already.
Yeah. And the original idea was that it didn't matter where we look. Once we found one, so we could stick to regions above the plane of the galaxy where there's less obscuration from dusk, for example. But these galaxies are well known and mapped out. So.
Did they come primarily from large sky surveys, by systematically mapping out, or they come from originally targeting things with funny photometry and magnitude, color magnitude distributions for their location on the sky?
I don't remember what Warren Brown was targeting when he first found the HSV1. It was something to do with white dwarfs, I think. So they were looking at the right blue blue colors, and I unfortunately I can't really answer that.
So
How did
being complete down to about 3 solar masses, stars in the halo. So
Yes.
in the SDSS footprint, he observed every single star
Oh, okay.
that would be above 3 solar masses. Theoretically could be a 3 solar mass star above.
Yeah, they have this blue color selection.
Yeah, they have a blue color.
Okay.
It's a color selection.
So they choose a color magnitude selection.
Yeah, and the things that fall into that are low mass white dwarfs, really weird low metalist galaxies, and velocity stars.
Okay, that's what I was trying to understand.
But they did not intentionally target for hypervelocity stars.
No,
No,
it's
for us,
part
no.
of a halo survey. The survey to the halo.
But this doesn't come from like Segway, the Segway surveyor.
It's from all of the Sloan Institute.
It's from Sloan, and he does follow up targeted it.
Yeah, he did single one star by star velocity.
Hey,
So what are existing hypotheses on other origins of hypervelocity stars? Are there random black holes flying around in the galaxies that do not happen to be at the center?
there are if I can quote you in the future, that's awesome. Random black hole hypotheses. Yes, if you have a rogue black hole, it can do the job. So people have postulated the existence of another smaller black hole in the galactic center, which would help. It would be a different mechanism than the binary disruption. The HSV3 indicates that the star actually came from a region closer to where it was observed out in the galactic disk, and there are 2 mechanisms that are potentially capable of ejecting a star with sufficient speed. One is if there's a star is in a tight binary and one of the partners blows up, goes supernova, and it basically is left free-floating and can have relatively high speed. Now, I talk about hypervelocity stars like this is amazing, that a star could be doing 800 kilometers per second. That's a little bit of an overstatement at some level, because the orbital speed of the sun around the center of the Milky Way is about, depending on who you ask, between 220 and 250 kilometers per second already. So there's rotation in the disk, so there's relatively high speeds available. So if something gets flung out at an additional 200 kilometers per second, it can sort of get bootstrapped to that higher speed. The other mechanism involves multiple stars and close encounters in sort of a hierarchical dynamical scheme. If you've got a lot of stars packed in a small space, one or a few can be ejected. So a high-speed ejection can take place dynamically, even amongst a few, maybe three or four stars. Those are the competitors.
For the 10 to the 6 solar mass black hole, the type disruption could contribute to a substantial fraction of this growth. So how about a 10 to 9 solar mass black hole?
Okay, so yeah, that's, I think, let me go there. Just if you keep the reservoir of binaries plentiful throughout the lifetime of the galaxy, you can build up a very, very a high mass in this mechanism. So with this magenta line, I have a prescription for reducing the density of stars in the galactic center of some arbitrary galaxy, and so I can keep a realistic stellar density, but if the stellar density remains high at early times and things are well mixed, you can continue to dump stars into this region of the black hole, and the same bathtub argument will apply. You'll end up accreting a lot of stuff. The tidal disruption event constraints, we don't see many tidal disruption events around other galaxies, indications that stars are being ripped up and eaten by black holes. Those constraints go away. This is just awesome. They go away if the black hole is bigger than 10 to the 8 solar masses, because the tidal disruption occurs inside the horizon. So there's no constraints. Put another way, well, that's... So it's reasonable, and I think one thing that we'd like to do is look for objects that have high stellar density, that are set up to take advantage of this route for feeding mass. And we have one such candidate. That was the one I showed at the very beginning.
Is there any possibility that a single star in an encounter with a black hole could be ripped apart and split out and divided into a binary?
Probably not divided into a binary, but that mechanism is exactly how we think stars wind up being eaten by the black hole. They get torn up, they get more and more bound, and the gas accretes onto the black hole.
If they get close enough to be torn up, they're finished.
Yes, and one of the questions that we have when we were first building these models is what fraction of the star winds up on the hole? Does stuff get spewed out as you were envisioning as another, sort of like many bazillion
No, I've
hypervelocity
done
atoms?
bits.
Yeah.
2 bits,
No.
and I get a couple of pretty good stars that way.
I think the density, the way stars are structured, it's more, and the way tidal forces work, it's more likely to rip off the outside and to leave a core than the other way.
How well is this studied with observations? I mean, not just this process, but any of these tidal processes, let's say, having stars just come close to the black hole and then they, I don't know, turn into a pancake for a while. And I would anticipate that they completely change their spectrum, their emission spectrum, and become hotter at least.
This is a hot topic in the snowpack conference last year.
Okay.
Anil, if you,
There's been about 10 observed possible cases of stars being disrupted around other galaxies, but they're so far away you can't actually do it. It's not like you can observe the star getting flying.
Okay.
Even in our own Galactic Center, you wouldn't be able to do that.
Right, but I would
But you can
anticipate
see,
the
but what ends up
spectrum
happening is
changes.
that you get something that's almost like a supernova-like energy event
Mhm.
that comes out because all of a sudden you're essentially you're disrupting the entire star. So
Right,
it's
I mean,
very
if you
similar.
think about the sun, there's a tremendous temperature gradient throughout the star, so if you break it or kind of, I don't know, squeeze it, then you should see that.
Yeah.
and
Yeah.
That was the disruptions in our.
Right, I don't mean you should resolve it, of course not, it's too small, but you can look at the spectrum and
Yes,
then,
yeah.
and then be able to.
There's going to be a HEAP seminar in after spring break that will be on the observational evidence for things like that. We just had a talk on theories.
If there are no more questions, let's start.